So welcome everybody to this university call today. We're going to be going over Quai 102. This is a modified version of Quai 102 that was presented last time. There's some changes and updates that have happened since this was originally presented. So we'll cover those. And with Quai 102, this is meant to be a more technical overview of how we're addressing our goal. So at the start here, we want to state what our actual goal is. So our goal is to address the tech limitations that exist with current blockchains to create a scalable global money that can handle all of human-based commerce. That's effectively the goal of Quai. So how do we actually go about doing that? We first need to define what that means in terms of technical requirements. So when we look at the technical requirement, we can look to the current number of payments to take place using credit card and debit card transactions. And then we can add some buffer onto that number. And we can effectively say that if we want to handle all of global commerce, we're looking at doing roughly 50,000 transactions per second. So that would then encompass things that are electronic payments, but also cash payments, at least for the majority of the developed world. So to understand how we can get to 50,000 TPS, we need to first go over the limitations of monolithic blockchains. So what are the physical limitations of monolithic blockchains? If we look at a first-gen blockchain, we can see that it's a very simple chain of events. So it's a single sequence that's progressing. There's asynchronous production of blocks, but there's only one agreement that's taking place at any point in time, which is how to extend exactly one chain or thread. And the issue that we have is that inconsistency at consensus causes delay. So what does that mean? If we think about a Bitcoin blockchain or a simple monolithic blockchain, take Bitcoin as an example, when a block is found, consensus is technically reached because that block has met the difficulty threshold to be appended to the chain with a new set of transactions or state transitions. The problem is we haven't yet guaranteed that consistency has taken place in the network, and more often than not, their network is going to be inconsistent even relative to the set of commitments that is made in that new block. So what does that mean? It means that I get a Bitcoin block from somebody that mined it as a node in the Bitcoin network. I look at that block and I see a transaction route or a state route. I need to be able to validate that block, so I need to be able to validate all of the transactions that are referenced in that block. But to do that, I have to have all of the transactions. The problem is there's no guarantee that those transactions, I yet have those transactions. Somebody has those transactions, somebody referenced those transactions, and somebody added them to what is becoming the canonical state by mining them into a block. But I have not yet seen them. So before I can append this block, I need to collect those transactions from my peers so that I can validate the block, which becomes a very expensive process. So what ends up happening is the fact that consensus is happening prior to consistency means that I will have a delay to become consistent prior to proceeding. And that delay is what ultimately limits throughput. And if I increase the number of nodes, I'll increase the amount of inconsistency. If I increase the number of transactions, I'll increase the amount of inconsistency. So if we look at nodes, the number of nodes in the network dictates how many hops I have to get around the network. And depending on the network topology, every hop will have a characteristic ping time. In the very simple example, if we have two nodes, to communicate that a new block is found and potentially to communicate that these transactions are found, I only have to go one hop from node 1 to node 2. It's a relatively quick process. But if we're talking about a decentralized system and I have 10,000 nodes, the number of hops that I will have to take is on the order of n log n. So for Bitcoin, say it's 10 hops, meaning if a block is found, it will have to roughly go through 10 nodes until everybody knows that that block was found. So that number increases with the size of n. So if I go from 10,000 nodes to 20,000 nodes, maybe that 10 turns into 12, so on and so forth. So if I increase the number of nodes, I'm increasing the amount of inconsistency because I'm increasing the time it will take for data to traverse the network. If I increase the number of transactions, I'm increasing the inconsistency because transactions are generated everywhere in the network all the time. But for us to then see those transactions everywhere in the network, we're still going to wait the number of hops and the number of times that it takes for a block, but for each transaction to, again, traverse the network. So if I increase the number of nodes, I increase my inconsistency. And in the same way, if I increase the number of transactions, I'll increase my inconsistency. If I increase the block speed, I'll also increase my inconsistency just based off the fact that every time I find a block, well, maybe that's not entirely true. Blocks don't necessarily increase your inconsistency. They just increase the time where your inconsistency matters. So the more often I have a block, the more time I spend after consensus trying to become consistent. So that's like the important time frame here is the time between consensus and consistency. So if I increase the number of blocks, I'm increasing the number of instances where I have a time where I have consensus and I'm inconsistent. So the faster blocks I have, the more inconsistent I'll be. But all of this adds up to delays and inconsistency limit throughput. So what can we do to address that? We can ultimately create subnet and shards. So instead of having 10,000 nodes, if I can take those nodes and divide them into subnets, and then have each one of those subnets represent a shard of data, I can decrease the number of nodes that are trying to become consistent with each other in that subnet, which means I will decrease the number of hops and decrease the latency. I can create scope. So again, with transactions, if I don't have to propagate the transactions to everybody in the network, but I can propagate it to a subnet of the network, those transactions will propagate faster in the subnet. And then I also can have different block speeds. So depending on the context of the state transition, if I can limit the number of nodes that have to reference that transaction or state transition, I can, for any sort of given period of time or block, I can have different block speeds in different subnets, which allows me to have larger subnets, the global sort of overlay subnet, that has effectively lower block speeds while still ensuring some amount of liveliness within the smaller subnets or shards. So subsets and shards will help us decrease delays. Fundamental point here. So addressing these limitations. So how do we use subnet shards and sets to solve the problem of scaling blockchain? And each one of these things poses its own set of challenges, and we have to answer all of the challenges that shards, sets, and subnets pose to be able to scale a blockchain. If we look at shards, the big one with shards is that we need to be able to shard state without sharding work or security. So what does that mean? If we have two chains and people are trying to finalize both chains independently, the chains can be structured in such a way that they can't make a commitment to both chains simultaneously. So the natural concept of sharding would indicate for every shard I have, I've also sharded my work or my security, because the security can only be put against one shard at any point in time. So if I have 2 shards, each shard will have half the security as if I had 1 shard. If I had 4 shards, I'll have a quarter of the security, so on and so forth. A big challenge, obviously. The other one is, how do the shards reference each other? So if shard A and shard B don't know about each other, but ultimately need to make transitions against each other or transfer state or transactions, how do they know how to reference each other? That's a challenge. And then within how do they reference each other, the question is, how do they reference each other in a way that they always guarantee that they're atomically synchronized? Meaning, if I have a rollback in A, but I don't have a rollback in B, there could be state transitions that were already sent to B from A that ultimately get changed due to the rollback, and B is unaware of that. So there isn't an obvious way to guarantee atomicity cross-chain. When we talk about sets, when we break the data into sets, the question is, how do I maintain a trustless, censorship-resistant generation of the subset of data that I'm committing to? And a great example of that is if you look at an L2, I think it was Optimism, they were talking about how they don't have fair ordering, or they don't have a mechanism to prevent their L2 from being DOSed with too many transactions. And their solution was to order them by proof of work, because effectively MEV bots were just submitting transactions, hoping them to get ordered or reordered. And they needed a mechanism to figure out fair ordering, so they added proof of work as a mechanism to submit something to their API, which is hilarious. But that's an example of how, given a subset of data, in this case, a commitment of in an L2 still needs to have a censorship-resistant and trustless way of aggregating transactions and ordering them in a set. And then the other thing that we need to do is we need to guarantee that the subnets are still decentralized. So there's no authority dictating the organization of the subnet. So there's a lot of challenges and problems to introducing these data science structures to solve the problem of how we scale. But the interesting thing is all of these problems can be solved with one thing, which is merge mining, interestingly enough. So what is Quai Network, and how do we use merge mining to accomplish scale? Quai is a hierarchy of merge mine blockchains called a braid. So there's 3 different levels. There's prime, region, and zone. So prime you can think of as this sort of main chain. Region is below that, and then zones are below region. So in this particular example, we have what we'd call 3x3 ontology. That's just referring to the structure, meaning there's 3 regions, and under every region there's 3 zones. And each one of these things has independent state. And there's actually been an update, fun news here. We'll still have a prime header chain and a region header chain, but because of PoEM actually holding state in prime or region has become superfluous. There's no reason to do it, because the guarantees that we're getting in zone from a security standpoint with PoEM are as good as anything that you would get in region and prime. So we no longer actually need to keep state in prime or region. So they'll still exist as header chains, but they won't actually have a state processor or a block. They'll just be a chain that's using to coordinate the zones. So the modification here is that each zone blockchain has independent state. The region and prime chains are header chains only. And the way that we coordinate this system is through the use of coincident blocks, which are blocks that are valid in multiple contexts. So they have the same hash in a zone, as they do in a region, as they do in prime. And we'll discuss how we accomplish that, but that's through merge mining that we are able to generate blocks that have shared hashes in multiple contexts. But once we have that shared hash, or that coincident block, every other chain now has an objective hash-linked reference to every other chain. And that's the mechanism by which we can coordinate multiple chains without having to have some secondary trusted mechanism of coordination. It also provides that atomic guarantee, because if data is able to be referenced via a coincident block, if that coincident block is rolled back, the data that was being able to be referenced is also no longer able to be referenced, which means in the destination, it will also roll back. So the coincident blocks force synchronized rolling forward and rolling back of all of the different zone shards. The other property here is that the zones are fully composable and interoperable. There's a shared token and monetary policy. This statement is actually no longer true. Difficulty increases no, that's true. That's true. So to do coordination here with the region and prime header chains now, we only want to have snapshots globally less frequently than we do locally in the zones. And the reason for that is because we want high performance in our local subnet, and we also want to eventually be able to reference that transaction globally. However, to be able to synchronize many asynchronous shards, we can't always be referencing the asynchronous shards synchronously, else they would no longer be asynchronous, and we wouldn't be able to get that performance benefit. So there's a delay between the referencing in zones to region to prime of roughly a factor of 10. So zones have 10-second blocks, regions would have 100-second blocks, prime would have 1,000-second blocks. And what that means then is that's sort of the sacrifice that you make through scalability, is that you're going to have to wait for one of those higher order blocks to be able to do a more globally seeable transaction. And what that means then is, because the difficulties have gone up, obviously the block times go up, again, proportionally by that factor of 10. And when we mine in Quai, we have to mine a prime, region, and zone. So a miner they must mine prime, they must mine region, and they must mine region, they must mine a zone, but they get to self-select the region, and they get to self-select a zone within that region. And what we call that is a slice. So if you take any three, prime, region, zone out of this hierarchy, you are effectively choosing a slice, and every miner gets to self-select what slice they're trying to produce blocks in. The other thing that's a property here is that all work is applied to prime, meaning when I'm in a zone, when a prime block is found, that prime block is getting the work that is added into the zone, and that zone is getting the work that's been added into prime from all other zones. So our security inter-prime block is the same as if everyone was just mining a single prime blockchain and the zone blockchains didn't exist. Intra-prime, you're still achieving security, you're just achieving it slower than you are when you're referencing into prime. So what is merge mining, and how are we using merge mining within the hierarchy of blockchains that is Quai? We have a merge mined header, and the block header describes the position of the chain, and it has data that is valid depending on which difficulty is met. So if we look here, if we're a miner, what we're doing is all the time we're creating proposals for what we think should be in this header for all contexts, because again, we must mine a slice, which means we must be proposing how to update the prime portion of this, the region portion of this, and the zone portion of this every time we're going to create a pending header to mine. And then what ends up happening is when we mine, we'll meet one or more of the difficulty thresholds at some point. If we meet the lowest difficulty threshold, which is a zone, we'll end up finding a zone block. And the data that's highlighted here would be valid, and the rest of the data we can think of it just as an extended nonce. There's no real commitment to it. There's no purpose. It's meaningless from anybody's context in any chain. It's just like a big piece of random data in the header as far as we're concerned. Now, if I get further lucky, I can meet the region threshold. And when a miner finds a region block, they're also necessarily finding a zone block. And so now the data that's included in the header that's both region data and zone data is now canonicalized and referenceable in both a region chain and a zone chain. And then finally, if we get a prime header, we'll also simultaneously find region and zone blocks, which means the entire header is used, the entire header is committed to, and the entire header is pertinent in 3 contexts. So the miner is only performing work in a slice, and depending on how lucky they get when they find a block, it will dictate what type of block it is within the hierarchy. And so how does this play out in terms of Quai and the propagation of transactions in a hierarchy? I think it's important to point out, just, obviously we've gone over this before, but when we're talking about the Quai hierarchy here, and we're talking about chains, from a user's perspective, if I'm doing a transaction in a zone, and it's an intra-zone transaction, meaning I'm sending some money to an address that's in my zone, that looks exactly like an Ethereum experience, so to speak. So, we have 10-second blocks. You do a transaction, you'll start to get a finalization guarantee within 10 seconds once it's included in one block, and that finalization will increase as blocks are produced. Now, if, for example, though I have a transaction that needs to go somewhere else in the hierarchy, I'm going to have to wait a little bit longer because I'm going to need one of these dominant blocks or blockchains to reference in such that my destination can see the transaction that I just made. So, for example, let's say that I'm trying to send money from this Cypress 2 block to Cypress 1. Cypress 1 needs to have a backward-looking reference to the transaction that's just happened in that Cypress 2 block. So the progression that happens here is Cypress 2 is getting mined. Now, when I find that region coincident block, Cypress 2 can now reference everything that was prior to that, including any transactions that happened in that adjacent Cypress 1 block. But for Cypress 1 to be able to reference Cypress 2, I have to keep going. And when I get to that coincident block, Cypress 2 now has a reference back, or Cypress 1 now has a reference back to Cypress 2. But I've also found a reference, it's not highlighted, but I have a reference into a prime dominant block, which actually provides me the ability to see any transactions that have happened in these prior highlighted blocks all the way back to Paxos 1 and Paxos 2. So you can see with time, everybody can see every transaction that's pertinent to them in the network. However, it takes time if we're going cross-shard in the network. From a user experience standpoint, you're just doing a transaction. It's just taking a longer time for that transaction to finalize. You have good finalization guarantees that that transaction will eventually finalize once it's included in any one of the zone blockchains. It's just you won't be able to re-reference that transaction until it actually is finalized in the destination. What that means is that, even if I have a transaction that's originating in Cypress 2 and going to Paxos 2, maybe, in this ontology, that takes 20 minutes to get there. But that's only 20 minutes for me to re-reference it. If I get 3 or 4 Cypress 2 blocks, I have strong assurances that that transaction indeed will be referenceable eventually in Paxos 2. So I don't necessarily have to wait to say that it's finalized even though it's not yet re-referenceable. So within a couple of blocks, I can still say, yeah, that transaction's finalized. I just can't re-reference that transaction in Paxos 2 until the dominant shares are found. So to give a summary here, the coincident blocks create hash-linked references between the chains. It's a stochastic phenomena, but it allows us to create cross-chain transfers without any sort of trust. The mechanism that we're using to extend the head, in this case PoEM, this proof of work is out of date, so it's PoEM, is the same mechanism that we're using to create cross-chain state transfers and transactions. But the important part is that we have independent chains. So the chains are independently progressing asynchronously from each other. And the subordinate chains don't need dominant state. And only at coincidence are we forcing synchronization. So every one of these zone chains has its own stochastic ticker that's creating its own blocks. And unless we see a dominant block, we don't care about anything that anybody else is doing. We're just managing our own state. We're managing our own transactions. We're just happily moving along. Only when I get a reference in a dominant block that allows me to reference data outside of my context do I care about what anybody's doing, or is any form of synchronicity imposed upon me with any other chain in the network. So this creates what we call the braid. And in the braid, when we talk about what is re-referenced or truly finalized, we talk about the finalization horizon. And anything that's sort of to the right of it, we call the fray, meaning you have transactions that are effectively still in flight that aren't re-referenceable in their destination. And then anything prior to that, we call the braid. Okay, so this is another thing that we need to do that is really important in terms of the information science and data theory of how to scale blockchains, which is we need to create an incentive for nodes and miners to do more than just create hash. If we think about Bitcoin and we look at what the reward function is for a Bitcoin miner, the reward function is strongly dictated just by wanting to generate hash and hash rate. There's little to no incentive for them to care about bandwidth or latency with it between their peers. There's a little bit, but it's very small, and we can see that because there's a very small set of orphans in the Bitcoin blockchain, given the transaction throughput that is allowed and the block times. So the miners have very little incentive to care about anything except mining, i.e. just producing hash on blocks. But if we want to scale, we need to change those incentives so that not only will we incentivize miners to process and secure the blockchain, but we should also incentivize them to figure out how to topologically self-organize. So in that prior slide, we were talking about how miners must self-select a slice. What they're going to want to do is they're going to want to find a peer set which has low ping times and low latencies relative to themselves, which means they're going to want to generically, topologically, or geographically self-organize into subsets. Because if I self-organize into a subset, I'm going to be finding peers that are less latent to me. And if I find peers that are less latent to me, that means I will reduce my uncle rate or my orphan rate. And if I reduce that, I'm proportionally increasing my total revenue. So if I have a 10% uncle rate and I can reduce my uncles to 5% by choosing region 1 over region 2, I've directly impacted my revenue by 5%. So in our system where they have a choice of subnet and they can choose that subnet, there's a strong incentive now to optimize their peer set and to increase their bandwidth and decrease data latencies. And we've actually written a paper on this. So the original paper, not the original, But the very original block reduce paper actually was very much focused on thinking about this just as a subnet problem and a data propagation problem within subnets, and figuring out how to create self-organized subnets that have incentive to optimize. Anyway, subsequently, we wrote a paper on it where we introduced the concept of HLCR as well, which is now deprecated. It's the head choice, but the concept that is explored in the paper is the impact of subnetting and what that has in terms of delays to data propagation, and ultimately the delay between consistency and consensus. So basically, the idea here is we have, a mathematical representation of what this hierarchy looks like there in figure 1 on the left. And then in figure 2 on the right, we're saying if we think about the blockchain and the nodes as an n by n regular graph of nodes, we can talk about how long it takes for data to propagate in that topology with that number of nodes. And we call that time here delta. This is capital delta. And that's on the order of n log n, where n is the number of nodes in the n by n regular graph. And if we subdivide that n by n regular graph, we can reduce the value of n, which will then reduce the value of delta, again, proportional to n log n. The other n term here is actually hidden in the CD term. But then the other thing that we're also doing is, because miners can self-select, they're going to be incentivized to reduce that lowercase delta number, which would represent effectively the ping times. So how many milliseconds it takes for one node to ping another node that it peered with. If we look at a global network and a global overlay like Bitcoin, that network will have, say, average 100, 150 millisecond ping times. And if we say Bitcoin takes 10 hops to get data around the network, just to propagate something that says hello around the network, will still take a second and a half. If we take an alternate topology where we subdivide and say into 9 shards, i.e. the 3x3 ontology proposed initially with Quai, I can reduce that n by 9. So I've taken those 10 hops and I maybe have turned them into 2.5 hops. Additionally, that delta, if the miners, again, self-optimize, you could expect the ping times to drop from, say, 150 milliseconds down to 10 to 20 milliseconds. So if it's 10 milliseconds and 2.5 hops, I'm at 25 milliseconds versus a second or more with the Bitcoin topology. So right there, you can see how just through creating the incentive to self-optimize the subnets, you can potentially increase your throughput by 50x just by decreasing your latencies by 50x. And the upshot of this is that subnets incentivize miners to self-select the best subnet and maximize rewards. So when we talk about picking ahead, this is a very important part of the process, and this has also changed. So we no longer talk about the hierarchical longest chain rule. We're using PoEM as the mechanism to pick our head. So HLCR is dead, and long live PoEM. And PoEM I went over last week, and PoEM stands for proof of entropy minima. And the idea with PoEM is that we'll use the intrinsic entropy of any given tip in our block to weigh and choose a head. And there's a couple different ways to try to interpret this loosely. If you want to get the in-depth analysis of how PoEM works, feel free to look up the last Quai University Call. But this is just a summary, and there's a mathematical interpretation of what we're doing. One is that we're measuring the likelihood of an event, meaning the likelihood of the existence of a certain chain or block. And we know that the production of a block is not an independent event because that block links back to a prior independent event, which now makes those two independent events dependent, right? When I say in my block header, this is my parent block, I have made that block dependent on the prior block. So because of that, when we do the mathematics and we're measuring the likelihood, we have to be doing combinatorics on dependent events, not independent events. That's really kind of where proof of work falls down. But then what we're doing is we're choosing the least likely head to be in existence. That's the mathematical interpretation. The physics interpretation, which I like the best given my background as an engineer, is that we're reducing entropy within the system, and entropic reduction is necessarily an expensive process. We're then measuring the amount of entropy reduced, and we're doing it in the most accurate way possible because we're measuring every share that is proposed and we are computing the entropy exactly. And then in the sequence, we are computing the total entropy exactly, which allows us to compare any given heads exactly, no matter what the context or share size. So previously the question is, how much is a region block worth compared to a zone block? And if we were thinking about that in a work-based context, we would overweigh the region blocks a lot of the time and underweigh the zone blocks. And we would create time-based withholding attacks because we weren't accurately measuring and assigning weight to each one of the samples effectively, which is the blocks. But with PoEM, we're accurately measuring that. So the number of bits of reduced entropy in a block is how much that block is worth regardless, and then adding up the number of bits in the sequence or computing the total entropic reduction in the sequence will always give us the exact result of the best head choice. The other thing that's super interesting about it is that using entropy creates a time invariant mechanism to choose head and coordinate chains. So what this means is that if Brenny mines a block, that block intrinsically has an entropy. It has a parent, and it has its own intrinsic entropy, and it has a total entropy dictated by the chain that it's pointing back to. So the second he mines that block, it has an intrinsic property which dictates my preference and how I would weigh that block against any other options before I ever even see his block. So he's dictated my preference, and I don't even know what the block is yet. I don't know that he's even mined it. But regardless of when I see it, if I see it a second from now, a minute from now, or 10 years from now, I will still have the exact same preference for it, and it will be identical to Brenny's preference. And that's the power of PoEM. Because our preference is always identical in the system always, that is how we get perpetually perfect consensus. And that's the only way that you can actually solve this problem of coordinating multiple chains with multiple asynchronous context. And that's why at the beginning of the call, I was kind of going back and forth with Brenny, just talking about how we've broken the FLP impossibility theorem, which is amazing. But what it allows us to do is, from a practical standpoint, is that we can coordinate an infinite number of independent chains or threads. That's what this says. Because I no longer have time to resolution. I don't have a time preference. So my choice and my consensus now, because consensus always exists, it like never exists and it always exists. If you run Quai code, like, you're in consensus because we never can disagree. Data that I have or data that you have or the time and the sequence in which that data arrives to me or to you does not matter at all. It's an independent process. It's a time-independent process. But what that means is that if we're always in consensus, the only thing that we have to worry about now is eventually becoming consistent. But that there's no limitation to what I need to do now in terms of becoming consistent. I just have to eventually become consistent. I could take a second to become consistent, or I could take 10 years to become consistent. It doesn't matter. I'm still going to be in consensus that entire time. The practicality of it is it would suck to take 10 years to get into consensus, but that's obviously, or to consistency, that's obviously a highly extreme example. But what it means is that the network is incredibly robust in a latent environment. And the only thing that suffers is hash efficiency. So in other blockchains, we could have the blockchains completely blow apart when they get 20% hash inefficient. right? Meaning that 20% of the blocks that are found are not put into the canonical chain. So 20% are orphans or uncles. The problem with orphans and uncles is that orphans and uncles beget more orphans and uncles, and they do so geometrically. So at some point, what you end up having is a blockchain that fractures, that keeps fracturing, that causes more fracturing, and it never can unfracture. And that kind of is a cascading failure that can happen around 20% hash inefficiency. The crazy part about PoEM is because we're always in consensus. PoEM can operate at 1% hash efficiency. There's no breaking apart of this chain. There's only a prolonging of the time it takes to become consistent. And there's a reduction in the actual applied security to the chain. But there's no process where the chain ever breaks, which is amazing. Like there's so much here, and people should go watch the other thing. But it's like such a simple equation. It takes everything that you should be doing. It is the way to like solve blockchain consensus. And every day that we're working with it, like we figure out something new. But it's so beautiful to watch because you'll see these nodes, different parts in the world, having these bad latencies. They'll lose connectivity for a second, they'll come back, and we never disagree. The second data arrives, we're still 100% in agreement all the time, and we're progressing instantaneously in the exact same way and state again. PoEM is absolutely magical. And one of the things to think about here is when we were conceiving this chain in the concept of HLCR, we were kind of saying like prime is dictating the choice. The dictation of the choice is at the zone tips. So the zone tips are just picking their best tip, and they're doing it independently of the other zone tips. And their only incentive for coming back together is that if they can reference a DOM share back into one of the other shards, they'll effectively be committing to that other shard's work and inheriting their entropy. So you can actually think of this system as a Hydra where you have many heads independently choosing their own path, but they're eventually pulled back together by the body. Yeah, anyway. So, and then in terms of network security, the security, again, this still says difficulty. This should say entropy. But if we think about the total entropy reduced over time in a zone, we're sort of reducing entropy at a certain rate. And then when we reference in another zone via a region block, we're inheriting that zone's entropy. So we'll see a step change increase in our total entropy at our tip. And then what will happen is if we think about the region block progressing or the region header chain progressing, that'll progress at a higher rate than zone because there's more entropic reduction taking place in more context. It's all getting applied to that region. So our sort of finalization is increasing at a higher slope. And then when we get one of these prime blocks, again, we'll get the step change up again, and then we'll also increase at a different rate. But the finalization here in all context exists. It's just happening at different rates. And then when we reference in one of these DOM shares, we get these discontinuous sort of adders. But at the end, we all end up convergent on the total entropic reduction in prime. So we eventually always get finalization guarantees that you would be getting if all miners were mining every transaction. It just happens eventually. So interprime finality has the whole network's hash security. And one of the things that's like super interesting here too is there's actually a real trilemma that exists that I don't think people talk about. We've argued in other presentations that we've broken the sort of description of the blockchain trilemma that Vitalik put forth. And, it's a little bit of a sophomoric description because it uses properties that can't be objectively quantified or determined, as trade-offs. So in an engineering problem, if you're going to talk about a trade-off space, and you're going to talk about a trilemma, each one of those points in the trilemma should have a comparable property, and that property should be able to be measured in a unit. One of the interesting things here is there still isn't a panacea. It's just we have a new engineering set of trade-offs that no one really has because of what we've been able to do by being in perpetual perfect consensus using PoEM, or by creating a hierarchy that runs subnets that incentivize node operators and miners to self-optimize the network and minimize latency. We end up in a new trade-off space, and it's actually a really interesting trade-off trilemma, which is, if we look at what we're actually doing and what we're actually doing in each one of the contexts, we're effectively trading these three properties. So we're trading network latency, we're trading memory latency, and we're trading computation latency. And these are the actual limitations of what is possible. So in any given context or structure, if I reduce my network latency, I can trade that for memory latency, or I can trade that for computation latency. So if I have a faster network, I can have a bigger state tree. If I have a faster network, lower latency, I can have more transactions and more complicated transactions. If I have less complicated transactions, I can have a slower network. If I have fewer transactions, I can have a slower network. If I have a smaller state tree, I can have a slower network, so on and so forth. So each one of these properties is all measured in inverse seconds, and they all have a different but roughly equivalent numerator of some sort, right? With latency, you would think about it with bytes. With computation, it would probably be operations, and then with memory, it would also be sort of operations. So, but in aggregate, there's a network bandwidth that's sort of defined by where you choose your point in this triangle, but you can trade properties in that engineering domain. And then the cool part with Quai is that with that hierarchy, we're trading different properties in different contexts to try to get optimization of all of them. But what this also means is that Quai is defining the physically limited frontier of what's possible in a distributed system that's trying to create a sequence of events, or blockchain. So what are the conclusions? A decentralized system can be built that can handle all of human commerce. Merge mining solves issues associated with sharding and security. And the trade-off for throughput is a delay in global consensus. I got to change that last one. That's a delay in global consistency. We're always in consensus. So anyway, cool. Any questions, Brenny?
Yeah, so we have a few here. So one question is, how long does it take per transaction from the time it was sent to the time that it is confirmed?
So that's going to look very similar to Ethereum. It depends on, again, what you pay in fees, how quickly it propagates. But, in Ethereum, you generally see a confirmation in 20 seconds, 10 to 20 seconds. So you'd expect a similar type of performance here.
Gotcha. And then another question is, could you please shed more light on how Quai Network solves the limitations of parachains, since parachains are subject to atomic block progressions and rollbacks?
We're talking about Polkadot here?
That's what it seems like.
So the issue with Polkadot and the issue with parachains is how you're referencing in and what you're able to do when you reference in. The biggest limitation that you're going to see is the fact that you don't have native currency in the parachain. And that's effectively their Achilles heel. And the reason they do that is because if you were to have native currency, if DOT was usable in parachains, the time that they would have to wait between the parachain and between the, what do they call it in Polkadot? It's not the beacon chain. Whatever, the main, the main Polkadot chain, you would have this like huge time you'd have to wait, just like going between an L1 and L2 in Ethereum, and they like get away with it by just like not letting you use dot in a parachain.
Gotcha. Cool. Well, I think that's all the questions that we have for now. So I don't know if we have any closing remarks.
No, I would just say I'm super excited these days. Watching the system is absolutely beautiful. We've accomplished a thing that nobody's ever accomplished. Right, so like people can try to push throughput in a chain, but like nobody's created a limitless ability to coordinate many. And we have been pushing to get this, and now we have it, and it's perfect. So it literally is limited only by network bandwidth. So there's a new orthogonal vector we have created, which is amazing. And we are going to exploit the hell out of it.
Super exciting. Super exciting.
So that's like why we've had delays in terms of, wanting to get to testnet, is because there's been about 7 or 8 problems that we had to solve. PoEM was the last of those problems, and they were pretty esoteric and difficult problems. But, we started from first principles, moved our way up, solved the next problem, solved the next problem, solved the next problem, solved the next problem, then finally got to PoEM, and PoEM is so beautiful to watch. Because, like, you don't even see uncles. It's amazing. I mean, you get uncles. You get uncles all the time. But, like, you don't even see it. So normally when you get an uncle, there's, like, contention. And you're mining here for a second and then doing this over there. You never, like, switch. Like, once your miner gets a block, it's going to continue mining that block because it already made, like, the perfect choice. So the only way it updates is if it gets a better block. So you don't see any uncled behavior or contentious mining ever. And we can add as many shards as we want and create as many latencies as we want. I mean, our baseline testing is that we spread nodes around all the different continents just so that we can have bad latencies. And then we juice up our block times, or juice down our block times to, 2 seconds for a zone block. And we're overlaying that on 400 millisecond ping times. And we'll produce 40% uncles, and we just don't give a shit. We just keep going. It's amazing to watch.
Incredible. Well, I know that
this is like a Toyota, like an old school Toyota Hilux. That's too old of a reference.
What do you mean by that?
So there's this truck that Toyota made that became sort of like very ubiquitously seen in developing countries like Africa and the Middle East, because it was just like so robust. It would just never break, and it got that reputation. And then Top Gear like caught on to this, and they made an episode, and they like tried to torture a Hilux and break it. They ended up like sinking it in the ocean, running it into a wall, lighting it on fire. And then the very last thing they did is they put it on top of a building that was getting demolished. It was like a 20-story building. They demolished the building and then found the Hilux, and like it still ran. But that's effectively what we have right now, is no matter what you do, this will always run.
The Hilux of consensus mechanisms.
Yeah, I mean, you could say it's high performance too, because like we get a bunch of throughput, but the more important property from an engineering standpoint is that it is a Hilux, man. It's so fun to watch because like you can just torture it, and it's just like, I don't care. You just, yeah.
Super exciting.
Yeah. So, yeah, we're finally there. So, like we're from a like testing standpoint, we're expanding like our tests now. So we're starting to test in a higher number of nodes with higher throughputs, right? And we're just like trying to break it now, like trying to push its limits. But I don't think you can break it. Okay, I'll do another one. It's like Bruce Willis in like the third M. Night Shyamalan movie.
Tell us, what's the reference?
Unbreakable, I believe, is the movie. Do you know about this? Man, I'm just turning into a dad. I'm throwing references out.
Yeah, dad mode.
That nobody knows about. These are all good movies, though. Like, all good references. Everyone should go watch that episode with the Toyota Hilux from Top Gear. And Unbreakable is a great movie. It was actually, there was like a 3-part series. They just recently released a movie with, it was like about like Glass Man, but it was like a 3-part thing. And they were all in this like mental hospital together, but it's this, they're all like heroes, but they're like anti-heroes. And it was Bruce Willis again, and then they had Samuel L. Jackson was the other one, and then I don't remember who the third character was, but that started with the movie Unbreakable, which again is a great M. Night Shyamalan movie.
Well, we have a lot of good references to now look at after this call.
I don't recommend bad movies, guys. So, like, if I recommend a movie, it's going to be worth watching. Unbreakable. Yeah. So, cool.
Awesome. Well, it doesn't seem like we have... The one other question that we have is when testnet?
We're expanding our tests right now. So we're pushing transactions. We're pushing, number of nodes in the network. We're pushing how far the network is. We're like pushing throughput. Right. We're running integration tests. So soon is the answer. We're gonna like red team this for a while. See if we can think of ways to break the system. But soon. It's going to be sweet.
Soon. All right.
Yeah.
Well, I think that's everything.
Okay. Cool, guys. Thanks, Brenny.
Cool. Thank you, Dr. K. And thank you, everybody, for joining.